Welcome to EDU World Space.
Here we're going to use Gauss's law to determine the electric field of an insulating shell that holds a negative charge on it. That shell is spherical with radius, let's say, r. And the idea in Gauss's law is that the electric flux through a closed surface, which is almost never an integral that you want to do, but you use symmetry to simplify that. However, that electric flux is proportional to the enclosed charge over epsilon naught. One of the consequences of Gauss's law is that a sphere of charge, provided the charge cannot move around easily, will behave as if it is a concentrated point charge at its center on the outside of the sphere. However, on the inside, I can draw a little Gaussian surface on the inside of the sphere, and there is no enclosed charge. So what that tells us is that when r is less than r, big R, the radius of the sphere, the radial electric field is zero. When r is bigger than the radius of the sphere, basically the radial electric field times 4 pi r squared, the surface area of the sphere, is equal to the total charge on the sphere, in this case minus q over epsilon naught. And so we can see that outside the sphere, the electric field behaves like a point charge centered at the center of the sphere. So what can happen is if you put a little positive test charge off outside versus inside, and here we're going to use F equals Q times E. On the inside of the sphere, the force on the charge, since there's no electric field, is zero. On the outside, the force is the product of the little charge and the electric field of the big charge, which has magnitude kq, big Q, over 4 pi epsilon naught r squared. And the direction on that force is directed towards the center of the sphere. So no matter where you put that little positive Q, let's put it over here, down below, the direction of the force is an attraction towards the center of the sphere. And of course, if it was a negative charge outside, it would be directed, the force would be directed away from the center. So the important idea here is that Gauss's law ensures that if you have a fixed charge distribution with spherical symmetry, if you're outside, that sphere will behave like a point charge.